Hello, my name is Adrian Joshua Ogi, matrix number F25A1836, and I am from the SFM program. I am the developer behind the Sustainable Food Security Modeling Initiative. This project bridges data science, calculus, and precision agriculture to optimize crop management in Malaysia. So that is my all for my self-introduction. Now I'm going to go into the summary of the chosen bioscience problem. This project addresses the challenges of optimizing the harvesting time for Malaysian oil palm or fresh fruit branches, where after pollination, the fruit bunch grows in a biological sigmoid curve over roughly 20 weeks. You can see over here. Uh, the problem is figuring out the exact biological peak before the fruit overripens and drops, which compromises crude palm oil quality. And to solve this, I developed this app which uses calculus. It models the fruit's total weight over time and uses its first derivative to pinpoint the exact week where growth velocity is at its maximum. So, for the importance of studying this bioscience problem is for national food and economic security, where palm oil is a staple agricultural export and global food asset, and maximizing it yields efficiency, directly secures supply chains. And second is for sustainability, where reducing agricultural waste by preventing the spoilage of overripe fruits while ensuring that the highest quality of crude palm oil is extracted per tree. So before we go into the chart, we will see the sigmoid growth function, where it is the model of the total weight of the fruit bunch over week, which is calculated by X, where, as you can see over here, the sigma growth function is 25, which is the carrying capacity. 0.4 is the growth rate coefficient under optimal Malaysian climate conditions, and 10 is the inflection point or the week of peak growth rate. And for the derivative, it calculates the instantaneous weight gain velocity or kilogram per week using the chain rule, where in precision agriculture, this derivative eliminates guesswork by showing exactly how fast the plant is synthesizing biomass at any given moment. So now I'm going to explain the chart. So in the first week, the bunch weight is 0.665 and the growth velocity is 0.259. And at its peak, which is week 10, the bunch weight is 12.5 and the growth velocity is 2.5. And it only starts to go down after that. So week 10 is the peak. So at week 10, the fruit bunch is hitting its absolute peak speed of development and it is gaining 2.5 kilograms of mass per week. This is the optimal metabolic inflection point where we should plant our harvesting teams immediately. For my final point, which is how do I make this HTML better or to improve the user experience, I would recommend adding dynamic input sliders for the model parameters, which you might ask why. For right now, the carrying capacity and the growth rate and inflection point are hard-coded into your JavaScript and math formula. However, real-world biological data changes due to seasonal droughts, pest infestations, or variations in fertilizer. Now, how do I implement this? I have to add a HTML range which inputs allowing users to slide and alter these variables and link them to update your charts dynamically, which allows us to update the chart in real time. That is all from me. Thank you.